This is a two-part solubility problem. We have first to calculate the solubility of this insoluble salt in pure water. Write out our balanced chemical equation. And our ice table. Okay, so every mole S that dissolves, we have S and S moles of our two ions. And we have KSP is equal to the concentration of silver plus ion and times the concentration of the chloride ion. So this is S squared. We can calculate S by the square root of S squared. So that's equal to the square root of KSP. And we get 1.342 times 10 to the minus 5 moles per liter. Okay, so that's our solubility in pure water. The next problem is to calculate the solubility of this same insoluble salt only in a solution containing the ligand ammonia. Okay, now we would expect that due to the formation of this soluble complex that the solubility is going to be greater in ammonia than it is in pure water. Okay, let's work it through. Okay, in order to form the complex, we have to first have silver plus ion in solution. And then once the silver plus ion is in solution, it reacts with the ammonia. It's dissolved. Noting from our complex here, we need 2 ammonias for every mole of sodium plus ion. So then we can make our complex. Now the solubility associated, or the equilibrium constant associated with the first reaction is KSP, and this is KF, formation constant of this complex. Okay, the net reaction we can get by summing these two dependent equilibria, and what we see is Ag plus is produced and then immediately consumed, so it does not appear in the net reaction. Can't forget our chloride ion here. So again, these are dependent equilibria. So we're going to get the net value of K, we multiply these two. So K net is achieved by multiplying these two values. K net is thus equal to 3.06 times 10 to the minus 3. Alright, so if we look at our net equation, we can write our equilibrium constant expression. K net is going to be the concentration of our complex. Oops, wait, let me leave room for my ice table. This is what we do here, initial change equilibrium. Alright, so we're going to have the ice table, so I'm just going to move this over. K net is equal to AgNH3 multiplied by Cl minus and divided by NH3. Its coefficient is 2, so that has to be squared. Okay, now for our ice table, initial concentration of NH3 is 3 molar, and We don't have any of our complex or our chloride ion before this reaction occurs. For every mole that dissolves, we're going to lose 2 moles of NH3, and we'll gain a mole each of our products. So equilibrium is the initial plus a change. Alright, so now we can substitute that in. So we have 0.00306, because that's our value of K, and equal to S, and 3 minus 2S, and that quantity is squared. Alright, so to solve this, we see that we have here a perfect square. Okay, and we can see that if I take a second to write this. So we have S over 3 minus 2S multiplied by S minus 2S. So to solve this problem, what we can do is to simply take the square root of each side. So square root of this side and the square root of the other side. The square root of 0.00306 is equal to 0.0553, and that's going to be equal to S over 3 minus 2S. So we simply have a bit of algebra to go through to solve this. We'll do a cross multiplication. This times this is equal to this times that. So 0.0553 times 3 minus 2S is equal to S. We'll use the distributive property to multiply this out. Times S equal to S. Now we need to collect like terms so that we can get all expressions dealing with S on one side. So we'll add 0.111 times S to each side. We have 0.166 is equal to 1S plus 0.111S, 1.111 times S. And we would find that S is equal to 0.1494. Alright, now that we finally have an answer for S, we can go back and answer the initial question. And the initial question here, way up here at the top, is to calculate the molar solubility of silver chloride, which we've just done. So the molar solubility of silver chloride in 3 molar ammonia is 0.15 moles per liter, okay, much higher than it was in the pure water.